We're going to start Chapter 3, which is all about vector spaces. In Section 3.1, we're going to learn the definition of a vector space and look at some examples and some non-examples. So, suppose V is a set, and define two operations on that set. The first operation is vector addition. We're going to refer to the elements in V as vectors. And for vector addition, for any two elements in your set, we want to define x plus y. And then we also want to define the operation of scalar multiplication. And this is for any element in your set V and any scalar. And what I mean by scalar is a real number or a complex number. If I don't specify, you're going to think of the real numbers. And scalar multiplication means that you have this product, alpha times x. So this operation is somehow defined. Now we want to define what a vector space is. So first off, remember that we had something called vector addition, where we have x and y and v, and then we have this x plus y. Now if this vector x plus y actually belongs to the vector space V, then we say it's closed under vector addition. If for any scalar alpha, and x being a vector, we had this product alpha times x. But if that product is a vector that belongs to your set V, then we say that V is closed under scalar multiplication. So we want these two properties. We want x plus y and alpha times x to belong to your set V. So if you have those two properties along with 8 additional properties, I'm going to show you all the properties. These properties are also listed in your book. I think it's page 115. So you don't really have to copy all of these down. What I would like you to do is to listen. You can copy them down, but like I said, they're in your book. Definitely pay attention to everything I'm saying about these properties, because you have to have all of the properties for your set V to actually be called a vector space. Okay, so the other 8 properties that you need, remember that you need these 2 properties and 8 more, are the following. First off, remember that x plus y, we want that vector to belong to the vector space. But this addition here, x plus y, we want it to be equal to y plus x. We want addition to be commutative. We also want addition to be associative. So if you have 3 vectors in your set, then we want x plus y, then adding z is the same thing as adding y and z and then adding x. The third property is you want an element called 0 in your set, and this element is unique, such that when you add x with that element, you get x back. The fourth property is for all vectors x in your set, you can find a vector, which we're going to call negative x, in your set, such that x plus negative x will give you that 0 vector. The fifth property is that if you add 2 vectors and then multiply it by a scalar, this vector that you're going to get that belongs to your set, it could be found this way as well, by taking your vector x, multiplying it by a scalar, taking the vector y, multiplying by the scalar, and then adding that together. So it's like the distributive property when it comes to the scalars. Now we're not defining x times y. We're not multiplying vectors together. We're only adding vectors and multiplying by scalars. The next property is that if you add 2 scalars and then multiply it with a vector, what you could do is you could multiply the vector with the 2 scalars and then add that together. Those should be the same. The seventh property is that if you multiply two scalars together, then multiply it with a vector. It's the same thing as multiplying one of the scalars, the one in the back, with that vector and then multiplying it with the other scalar. And the last property is that you're going to have this scalar, which is the number 1. And if you multiply your vector by the number 1, you should get the vector again. So if you have all 10 properties, these 8 properties I just showed you, plus the 2 involving it being closed under vector addition and scalar multiplication, then your set is called a vector space. And the elements of your set are called vectors. So let's look at some examples. This is an example you're probably the most familiar with. Let's say you have the vector space R3. So these are vectors that look like this, where x1, x2, and x3 are just real numbers. So they're vectors in three-dimensional space. And you've probably referred to them as vectors before. And that's because this space, the set of all elements in three-dimensional space, are vectors, and they're in a vector space. And in general, this works for Rn. So you could have, R10 here and have 10 numbers, so a 10 by 1 matrix, and with the entries being real numbers. So our field of scalars here, again, if I don't write it, it's going to be the real numbers. I'm going to show you that this is actually a vector space by showing you it satisfies all 10 properties. Okay? You have to check every single property in order to say that this is a vector space. I'm going to show you the work that goes into this. So let's show it's a vector space. Now, we're going to let x and y be vectors, and sometimes people write them with little arrows above when you're dealing with a vector space. But we're going to say that if x and y belong to V, then we can write them this way. You can also write them just so that it doesn't take as much space. Some people write it like this. This is just the transpose of this matrix, which is exactly this. I'm going to write it like this, again, so I don't have to use so much space. And I'll also drop this transpose because it's the same thing. Now, how we define vector addition. So remember, you have to have some kind of addition. And how we're going to add vectors is we're going to say that adding these vectors, you're familiar with this. This sum is x1 plus y1, x2 plus y2, x3 plus y3. That's how we define vector addition. And then for a scalar in the real numbers, we can define alpha times x in the following way. We send alpha to every single thing inside this row matrix. So since we have the two operations, we have a set. Is this a vector space? So the first thing you want to ask yourself is V closed under vector addition? So in other words, does x plus y belong to V? Remember that x plus y, you can write it like this or how I wrote it before. Is x1 plus y1 a real number? Yes, if you take a real number and add it to a real number, you get a real number. All of these are real numbers. And let's review what this set looks like. Looks like this. These are real numbers, so it belongs to the set. So this is true. Is V closed under scalar multiplication? So this vector, alpha times x, you could write it like that or how I wrote it before. Does this belong to the set? Well, if you take a real number and multiply it by a real number, you get a real number. All of these are real numbers. There's 3 entries, so it belongs to the set. If we add x with y, is it the same thing as adding y with x? Well, let's see. X plus y, we said was, I'm going to stick with this notation. We said that this is x1 plus y1, x2 plus y2, and x3 plus y3. But with real numbers are commutative, so we can switch their order. This is equal to a y1 plus x1, y2 plus x2, y3 plus x3, and by definition, this is equal to y1, y2, y3 plus x1, x2, x3, which is y plus x. So x plus y is y plus x. This is correct. We want to show that vector addition is associative. So if I have 3 vectors x, y, and z, does the left-hand side equal the right-hand side? And here I've written everything out already because this takes a lot of time. So the first part is adding x and y together, then adding z. I define z as z1, z2, z3. So just following what it says here, we add these 2 together first. I get this. And then we add z to it. Well, if you add z, you're taking this addition, the sum here that you've already found, then adding z, that's why I have parentheses here, plus z1 plus z2 plus z3. But these guys are just real numbers, and you know for the real numbers, you can move the parentheses around. So that's what I did. Move the parentheses, and now you can see that x1, x2, x3, we can pull that out. And this is x plus y plus z. So vector addition is associative. The next property was there's a vector that we call 0, such that when we add 0 to any other vector, we get the vector x. So for example, in our space, 0 is this vector. So if we have x1, x2, x3, and we add the 0 vector, well, following the rules of vector addition, these are real numbers. Any real number plus 0 is that real number. And you do get the vector x. The 6th property is for every vector in your set, there exists another vector such that when we add this vector x with this other vector negative x, we get the 0 vector. And this is true if x is x1, x2, x3. Negative x is going to be negative x1, negative x2, negative x3. This vector exists in your set because the negative of a real number is a negative of a real number is a real number. So it does exist in the set. And if I add x with negative x, I get x1 plus negative x1, x2 with a negative x2, x3 with a negative x3, and this is 0, 0, 0, which is your 0 vector. The seventh property is that a scalar distributes. So we're going to check this. Alpha times x plus y is alpha times x1 plus y1, x2 plus y2. We've done the sum already. x3 plus y3. Send in that alpha following the rule of scalar multiplication. This is alpha times x1 plus y1, alpha times x2 plus y2, alpha times x3 plus y3. And now, because we know that this distributes when it comes to real numbers, this is alpha x1 plus alpha y1, alpha x2 plus alpha y2, alpha x3 plus alpha y3. And then we have this sum, you can see. So this becomes alpha x1, alpha x2, alpha x3, plus alpha y1, alpha y2, alpha y3. And now this is the product of alpha with x, and this is the product of alpha with y. Now you might want to ask, hey, can't I just skip all of this? All of these things? It seems like it's obvious. Well, it turns out it is kind of obvious for this case, but it's not obvious for, I guess, more complicated vector spaces. So you need to only follow the rules. Like, I have to send this into everything. And then from what I already know about real numbers, I can distribute this. But don't just assume you can distribute it without checking every single step. Okay, the eighth property I've done already for you. This is if we add two scalars together, then multiply it with a vector. It's the same as this. So you can see here I'm following the definition. This times this vector would be sending this into everything, dot, dot, like that. But then at this point, I know that because every single here is a real number, they're not like vectors anymore. The outside, all of it is a vector. So then we can distribute this like you see here. And then here I have our vector addition, so I can break them up into two pieces. And then I can pull out this alpha and this beta because that is the scalar multiplication definition. And you can see that I do have alpha times x plus beta times x. Yes, a lot of properties. The ninth property I've done for you. You can see that we want to show that alpha times beta, multiply them together first, and then multiply by the vector is equal to this. So I start with the left-hand side. I follow the definition of scalar multiplication, so send it into everything. Then here we're working with real numbers, so I can move the parentheses around. And then I see that I have this alpha on the outside of every one, and that's our definition of scalar multiplication. And then scalar multiplication again. By the way, I don't think I mentioned this, but this symbol right here means for all. So I want to show, my last thing I have to show that this is a vector space is if I take the number 1 and I multiply it with this vector, I get the vector. So let's see, 1 times x1, x2, x3 is 1 times x1, 1 times x2, 1 times x3, which is x1, x2, x3, which is x. So that one works. Here's a non-example of a vector space. So everything we did, where we said we have a set V that's equal to R3, or you could generalize this to Rn just by having n entries. This is actually not a vector space if you work over the complex numbers. Remember, complex numbers looks like 3 plus 5i or something like that, where you have real numbers here and an imaginary part. Why is this not a vector space? Well, remember that V is a set of, I guess you could say, I'm going to keep it the way we've been doing it. So it's the set of all vectors that have real entries. If I take a complex number, let's just take the complex number I, and I multiply it with a vector using the same definitions of scalar multiplication and vector addition that I had for the last problem where V was equal to R3, what would this be equal to? This is equal to I times x1, I times x2, I times x3. But now these guys are complex numbers. They belong to the complex numbers. They don't belong to the real numbers. So the problem here is that we're not closed under scalar multiplication. You have to have the real numbers here. You can't use the complex numbers. So you can't use a bigger set for your field that you're working with the scalars. And you know, this could also fail other properties as well. But you only have to check that it fails one property. If it fails one property, then it's not a vector space. So you just need to find the one property it fails. Checking to see if something is not a vector space is a lot easier than checking to see if something is a vector space. However, the way we could fix this is if we set V as the set of complex numbers, so C3. So if V is equal to all vectors that look like this, where x1, x2, and x3 belong to the complex numbers, then it is a vector space because it's not going to fail this the scalar multiplication. Complex number times a complex number is a complex number. So here it will work.